We are looking here at a most important video and an interesting one. I am Mr. Ish. Thank you for joining me. We are looking here at epicycloids. Picture the fact that you have a large circle here centered around the origin and then a smaller circle positioned along the circumference of that larger circle. As this circle rotates, it will trace a curve, and we are looking at a specific point here, P. If you were to trace this, you will generate what is called an epicycloid, which is generated by a small circle turning along the circumference of a larger circle on the outside, not on the inside. The epicycloid curve has a bunch of varieties. Consider what I'm putting over here. Capital R is equal to lower r k. What am I talking about? This large circle has a certain radius, we'll call it capital R. This small circle has a smaller radius, we'll call it r. There's a certain ratio, k here is equal to r over r. The ratio of the large to the small. Based on that ratio, you can have a different form of an epicycloid develop. When you are looking at a basic representation of a epicycloid, you have a circle over here. Here's my point. If you start moving this, there's no sliding, there's a movement of the small circle over the outer one. As you start moving this point right here will trace based on this ratio. You can have cusps develop, and the word right here is cusps, and it depends on how that ratio is. You'll have a different number of cusps. If you are assuming r here, the large radius, to be larger than the smaller radius, and that factor over here k is equal to 2, then what you have is a curve which traces, and it looks like this. A epicycloid is what it's called. That's when your k value is equal to 2. Now consider this as well. When you have your large circle and then you have the small circle, in this particular case, if the k value is equal to 3, and how are you getting a k value of 3? Here you could say the large radius was equal to 3, the small radius is equal to 1, so you're getting a k value here of 3. In this particular case, now when you trace this point, you're going to develop a different form of an epicycloid, and you'll have 3 cusps develop. Here's one cusp, here's another cusp, and here's a third cusp. These right here are called your cusps. When your k value was 2, you had 2 cusps. One was the large one here on top, the other one was on the bottom. It all depends on that k value. Let me show you one more, then we'll get into the essence of this video. In the particular case where the k value is equal to 4, now you'll have 4 cusps develop. The k value represents how many cusps develop. In this particular case, when you have a smaller circle and you're tracing it, you're going to have 1 cusp here, 1 cusp here, 1 here, and 1 here. This is exactly as a small circle is turning around the larger circle. It all depends on the k value. What would be the instance or the case when k value is equal to 1? In that particular case, you're looking at 2 circles of equal radii. In that case, you have this. Capital R is equal to small r. K value is equal to 1. Now, when you do the rotation, you have 2 equally sized circles. In this particular case, you only have a single cusp develop, and your curve would look something like this. And that's what it would be. A single cusp. Again, it depends on the k value. If the k value, which is the ratio of capital R to lower r, technically large radius to small radius, the k value will define that ratio, and it will define the number of cusps that you will see. Each of those cusps is part of your epicycloid curve. In this video, we're looking at the parametric equations which define the epicycloid. Our representation will begin such as this. X and y axis, the center. We have a certain large radius, we have a certain small radius. Connect the 2 centers of the circles, and that's what we have. We have a large radius, we have a small radius. From here to here is a small radius, from here to here is a large radius. It's certain angle, and you know this thing is going to move around. There's not going to be any sliding. It's actually going to rotate around this. No sliding whatsoever. And we are looking at this small radius here. We need to determine point P. But if you look here, it will get rather busy. If you draw across here and you draw down over here, you've generated a rectangle. But that rectangle is going to get messy, which is why I'm going to take that representation and represented it for you right over here. It'll be cleaner and it'll be easier. This point here represents this origin. This corner right here represents the center of this. We have, in essence, a connection between the two. From here to here, we can say this is my large radius. From here to here, we're seeing my small radius, and then we're seeing an arc develop and extend out this way. As you can see, I should make this arc a little more plausible because it looks too rough. This is what I have right here developing over here. And then the small circle obviously is looking, as you can see, right over here. That is this rectangular box pictured out for you. Now you have a certain angle theta. you have a certain angle theta here because these are parallel lines cut by a transversal, so that angle must be equal to that angle. My point P represents right here on the small circle. It is what's going to trace that epicycloid. From this center, I'm generating a certain radius, and we'll call this angle an angle alpha. Now you have everything you need in terms of a representation to get started. Right angle, right angle. We need to determine this point P. We are looking here at a certain x dimension, and I'm calling that x prime. From this origin, we're looking at a certain y prime away. But this point P, if you connect it upwards and then across, from the center of the small circle to this point, we're looking at a certain x units across. From this center of the small circle to here, we're looking at a certain y units across. But this point P, which represents the point which is going to trace, it has a certain x value, and I'm going to call that x double prime, and we'll call it y double prime. These are not derivatives by any means. I'm just differentiating the various x's and y's. How am I going to get the parametric equation for this and this? That is the task, and that is what we need to determine here for you in this video. To get this px double prime, I'm going to take this length x prime, and I'm going to minus from it x. To get the point y double prime, I'm going to do y prime minus y, because it will give you exactly here. Think about your x values. Your this x minus the x from here will give you the leftover portion, which is the x you're interested in. Likewise, the y from here to here minus that y will give you the amount from over here to right here. So these are all the issues which are coming into play, and yes, I understand it becomes messy, but this right here is our template right over here, which will give us our parametric equations. Now that you see everything, what we need to do is get to work. The first thing we're going to do is determine x prime and y prime, which is based on the distance from the origin, and we have a certain angle theta, we have a certain angle theta. If you look here at the x prime value from here to here, we can easily determine it because I have a right triangle which is developed over here, and you can see it. I can say cosine of theta is equal to x prime divided by the hypotenuse, but the hypotenuse is a combination of two radii, r plus lower r. Now I can do sine theta is equal to y prime over r plus r, and you see it. When I want to determine this height, I have this angle, and I have the hypotenuse, which is made of large radius and small radius. You can solve for x prime and y prime, and let's do it. When I do x prime, I'm getting here r plus r, so large and small radius times cosine theta. When I solve for y prime, I'm transferring this over here, I get r plus r times sine theta, and we have that determined. Now the only thing we need to determine is this x and this y, and we can easily do it. How will we do it? Look at this representation right over here. You have a right triangle that's developed, and it looks like this. This right here is the center of that small circle. As you see, it has a certain radius, which is r. It has a certain angle over here, which is alpha, but it also has a certain angle here, theta. So this angle here, as you can see, is alpha plus theta. That angle is equal to theta plus alpha. I have a certain x value, I have a certain y value, and they're 90 degrees. And we have everything we need now to determine these x and y values. With regards to the x value, the distance from here to here, we have cosine theta plus alpha is equal to x over small r. With regards to the y, we have sine theta plus alpha is equal to y over r. And you would solve in each instance for an x and a y, and we can. And I'm going to put them for you right over here. X here is equal to what? You push the r onto the other side. I have r times cosine theta plus alpha, and y is equal to r times sine theta plus alpha. For cleanliness reasons, I'm pushing this out, meaning I'm erasing it, because you've seen how everything has come about. The only thing which I'm keeping for you is this item right here on the bottom, which is giving me the points P. As you can see, the template is already in place for you. You just have to minus the 2. But before we minus the 2, we'll do one last thing. Look over here at this angle theta and the arc it's obtending. It's called this arc right over here, and I'm calling that, the arc length is S. I'll call that S and capital R. Why? Because it's the arc length developed by the large radius. Look over here at this arc length over here, and I'm calling that the S, but developing from a smaller radius because a smaller circle. But because when you're developing the epicycloid curves, you have the small circle rotating around the large circle. At any instance, based on these angles, these arc lengths must be equal because there's no sliding involved. The arc lengths must be equal. In general, arc length is equal to r times theta. the radius times the angle subtended by that arc length. And in each instance, for here you have a r theta. For here you have an angle which is alpha and r, but let me write it in terms of radius and angle, and it will be small radius and its angle. You know r theta is equal to this r alpha. You're going to solve over here for alpha because I'm looking here at theta plus alpha. I want to get rid of everything in regards to alpha and bring my parametric equations with regards only to theta. I know alpha is equal to r theta over r. This right here is my unifying factor, which I'll bring into play. Now you have seen the development of this, the development of these x and y values and x prime and y prime values. Now we have to look at the x double prime, y double prime, which will give me this point here. This point P has a certain x and y, and these are right here, x double prime, y double prime, and we have to do our minusing. What is my x prime value? It's right over here. I have r plus r and then cosine theta minus my x value, which is this, or cosine theta plus alpha. Again, why do we even have this representation, x prime minus x and y prime minus y? Because originally we developed the x prime values from the origin. The x values are being developed from the center of the other circle. The difference of the both is giving you the distance from your origin to this point P in terms of the x dimension and in terms of the y dimension. Hence, there's a difference coming into play. Now let's look at the y prime. Y prime value is right over there. We have r plus r sine theta, and then my y value, which is right here, is my r sine theta plus alpha. Now let's get rid of this alpha. I know alpha is equal to r theta over r, and we can bring it in. Let's do a little bit of math on the side, and we'll bring it in a unifying manner. You don't need to see this anymore, this representation, so I'm going to erase it because it has served its purpose. Look specifically in these items which I'm highlighting for you. I know I have theta plus alpha, cosine theta plus alpha, sine theta of alpha. This right here represents a union of angles which are impacted by the trigonometric functions. Theta plus alpha is equal to theta plus this, r theta over r. Common denominator, I have a r theta plus capital R theta over r. Isolate theta, I have a theta times r plus capital R over r. This right here represents exactly the item which will come over here, and let's bring it in. And that is the last step for our development of the parametric equations. And let's bring them out for you. The parametric equations are these. The point which is tracing the epicycloid curve, which I've represented as x double prime, will be this with the modification coming through. I have a r plus r cosine theta minus r cosine, this angle being represented in a way in such that the alpha has been removed and everything is with regards only to theta. You can say r plus r over r theta. You can write it as that way, nothing wrong with that, it's perfect. The y value in terms of the parametric equations for that point which is tracing is this, r plus r sine theta minus r sine, and then bring it in here. The alpha is removed, everything is expressed with regards to theta, r plus r over r times theta. And these are your parametric equations, one right here and one right here. The x and the y value of that point P which traces the cusps of the epicycloid based on the k value. Whatever the k value is, that's the number of cusps that will develop, and it'll give you your epicycloid. Remember, the epicycloid develops as the smaller circle traces along the circle's circumference, but on the outside versus the inside of that larger circle. If the k value is 1, then you're looking at two circles where tracing is such that the circles have equal radii. But in most cases, the large radius is always larger by a certain factor than the smaller one. Then you have the cusp development, which is appreciated by students. This right here is the end of this video. Thank you for watching.